Let's suppose that a particle moves in an elliptical path as shown. The position function is 8 cosine t I hat plus 4 sine t j hat, and then there is no third dimension component. It's just a 0. So this is going to be a two-dimensional ellipse that this particle follows. First, I'm going to fill in where it's located at different times. The first one's already done for me here. It says that at time t equals 0, our particle is located at 8 I hat. If I were to plug in pi over 4 here, I would get 5.7i plus about 2.8j. Okay, so that's going to take me to right about here. If I plug in a pi over 2, we'll get 4j. So we're located here. Clearly this particle is moving counterclockwise around the ellipse. And we can fill in the rest here. And we come back to 8i. Alright, what I'd like to do next is I'm going to find the velocity of this particle. We know that the velocity is always going to be tangent to the path. So if we were to zoom in on one location here and then see where our particle is located next, in the next instant it's going to be located above where it was before. So we want to see that the velocity at that point is in the positive j direction. It's going to be up. The calculus will reveal this. So first, let's take the derivative of the position. We'll get negative 8 sine of t in the I direction. And then we'll get plus 4 cosine t in the j direction with no k component. What I'll do next is I'll plug in the times into this velocity formula, and I'll get my velocity vectors. So at time t equals 0, we're actually going to have positive 4j. So if I draw that, I attach my velocity vector to the dot, which shows where it's located. And we just want a positive 4 in the y direction. Okay. Now our velocity is always going to be tangent to the path. But when we get to the top of our ellipse, our velocity ends up being negative 8i. So clearly we picked up speed. Particle is moving faster at this point than it was at that point. Okay, great. I drew the velocity vectors. Now we want to see what the acceleration vectors look like. So let's do the calculus once again. Take the second derivative of the position function. We'll get negative 8 cosine ti minus 4 sine of tj. And I'll go ahead and fill those values in. All right, so our acceleration vector has to be attached to the particle, and it has to go in the direction that our formula had said, which will be to the left, and it has to have the right length too, 8 units. So that's interesting. Our acceleration vector here points in toward center. And that's going to be the case here for all of the different positions. What I want to do next is I want to sketch the tangential acceleration and the centripetal acceleration. Now, interestingly, if we were to do this at just A, notice that our total acceleration is totally perpendicular to the path. There's a 90-degree angle there. So that means that at that point, the total acceleration is the centripetal acceleration. But what about at that next point that we had examined? What about here? The calculus showed that the total acceleration, which could be called a total, points in toward the center. Can we create components out of that which show the tangential and centripetal acceleration? If we draw a tangent line to the path, this angle here is not 90 degrees. So the total acceleration at that point is not equal to the centripetal acceleration. If we want the centripetal acceleration, we have to draw a 90-degree to that to see what would be perpendicular to the path. And then we have to project our acceleration onto that. And this will actually be called the centripetal acceleration. If we make a rectangle out of the thing and do another component here, then this component will be called the tangential component. So what this shows is that the total acceleration breaks down into two components, the centripetal and the tangential. They're always going to be 90 degrees to each other. Now what happens at B? Well, at B, the total acceleration just points down. And so once again, that is a centripetal acceleration. However, if we go all the way around to, let's say, this point, we see that our total acceleration points in, but it is not perpendicular to the path. We want to draw that tangent to the curve. And we just want to project this back with a 90-degree angle so that it hits our tangent. We want to find a component that is tangent to the path, and we'll call that A tan. There's also a component which will be perpendicular to the path, this one here, and that will be the centripetal component of the acceleration. So the tangential and centripetal components are just a new way of analyzing the total acceleration vector. The tangential component will tell us where our particle is speeding up and when it's slowing down. So in this case, our particle is speeding up. How do I know that? Because the tangential component is in the direction of motion of our particle, which is going to make it go faster and faster. The centripetal component, on the other hand, just changes the direction of our particle, but it doesn't make it go faster or slower. So let's answer the questions here. At what points or intervals is the particle slowing down? Well, that would be from B to C, and also from D to A. If we look back at the diagram that we had drawn earlier, so at point A, the length of our velocity vector is 4. But at point B, the length of our velocity vector is now 8. So clearly, our particle was speeding up. From A to B. What happened from B to C, though? From B to C, we started off with a high speed of 8, and now we have a speed of 4. So it was slowing down there. Then we go from a 4 up to an 8 again. So we're speeding up. And we go from point D to point A. We go from 8 down to 4 in speed. So we are slowing down here. All right, where would there be no centripetal acceleration? Interestingly, there is always centripetal acceleration here. How can you tell? Well, the path is curved, and our object never stops moving too. So there must be some centripetal acceleration causing the path to curve. At what points or intervals is our particle's speed not changing at all? So that would be at A, B, C, and D. How do we know it's not changing? Well, if you take a look at A, for example, the acceleration is totally 90 degrees to the path of the particle. The centripetal acceleration can't change the speed of the object. Here, there wouldn't be a tangential component. And the same would be true for B and C and D. Where would there be no tangential acceleration? At those same points. A, B, C, and D. Lastly, we want to find the speed as a function of time. We already have, from previous work, we have a function for the velocity, but that is a vector. Let's get that formula. It's negative 8 sine t I plus 4 cos tj. All right, right now it's not a speed, it's a velocity. So what we'd like to do now is we'd like to find the speed using the magnitude formula. The speed is nothing more than the magnitude of the velocity. And so what we want is we want to take the square root of the Vx and Vy. Now, in many cases, you don't have to do anything more than that. That's something that we could plug into a graphing calculator and then be able to see what that speed is doing as time goes on. Here I show some of the steps of just simplifying it to a little bit simpler form. But I did plot it, and as you can see, as time goes on, we find that our object has a speed of 4 at the start of the clock. It rises up to a speed of 8 after pi over 2 seconds. It comes back to 4 and goes up to 8. And all this should agree with what we see in the diagram here.